You basically get to drop a building on a tiny sample.
Yeah. You're listening to The Cosmic Cast. Hello and welcome to another episode of The Cosmic Cast, brought to you from the Earth and Solar System team at the University of Manchester. I'm John Pennyfisher and I'm joined with the usual co-hosts of Tom Harvey and Marissa Lowe.
Hiya.
Hello.
And joining us in person, a real treat it is too to be sat around a table recording a podcast in person with Dr. Ed Baker.
Hello.
How's it going?
I'm pretty good, thanks. How are you?
Yeah, not too bad. Thank you very much for joining us in person. You've just started, joined us here at Manchester as a postdoc. But before that, you were at the University of Oxford, I guess.
I did my undergrad and PhD there in the experimental petrology lab based there.
Cool, right. So I guess you had a PhD then, all experimental petrology stuff. I think we've talked about experimental petrology quite a bit recently. I was reflecting on the last episode that it's become a bit of a trendy subject at the moment.
Well, that's what this podcast is for, isn't it, John?
Yeah, we're very much on trend when it comes to planetary science type endeavours, that's for sure. Yeah. But anyway, sorry, to get back to the hard-hitting research you were doing then, Ed. So you did, so you were doing mostly lunar stuff, weren't you, I suppose?
Yeah, so the question the thesis was trying to answer is, given the observations of the refractory isotope similarity between the Earth and Moon, sort of how far can you push that? Could it be the case that you can explain the observations we have of the surface of the Moon, starting with a pyrolytic lunar magma ocean composition, that is a composition based on some of the Earth's mantle?
So I guess traditionally people do a lot of modelling using quite a unique starting composition rather than terrestrial-based compositions.
Yeah, so over the years there have been a whole bunch of different models for the bulk composition of the lunar magma ocean, and sort of, I guess through time they've sort of trended from being more iron and refractory element enriched to sort of less so, and mine was one of the many models that have been done with a purely terrestrial starting composition.
Okay, so to take a step back, what are refractory elements and why are they useful to look at?
So refractory elements are elements whose 50% condensation temperature is, I think, above 1500 Kelvin.
Okay.
I'm not sure about that though.
I guess it's just stuff that's hard to melt, basically, isn't it, really?
Yeah, so it's elements that are found in stable compounds that would have formed solids early on in the solar system, and so would be found in the inner solar system.
So I guess things like olivine is a refractory mineral because it's difficult to melt. It's like the last thing to melt when you do partial melting in the mantle and stuff, isn't it, I guess?
So like the opposite end of the spectrum of to quartz, say.
Yeah, exactly.
Got you. Okay.
Yeah.
Well, that's pretty interesting, though. So I guess, because I guess no one's done that before, have they? They've tried. No one's as far as I can recall, have tried to model lunar stuff using a sort of a terrestrial type composition.
So there was a 2018 Charlier et al. Paper which came out a couple of years after I started my thesis.
Always useful.
Always good. But no, I think in the last, let's say, 10 years, there have been a couple of attempts to either experimentally or to sort of combine experiments with some modelling to examine a terrestrial lunar magma ocean.
So what sort of model were you using? Was it based on experiments? Was it a numerical model or?
Yeah, so mine was entirely experimental. That's one of the things that sets mine apart, because I take a lunar pyrolite. I do actually subtract 20% olivine by weight, because olivine is the liquidus phase, and so it's well understood how that would crystallize, and so there's not much point examining that bit in particular. And then I just do 11 equal mass steps experimentally, where the melt composition of the previous step sets the bulk composition for the next step.
Okay.
So I'm sort of iteratively
just building up a sequence, I guess.
Building up a sequence.
Yeah. That's really cool, though, isn't it? I think that's one of the things I really like. I like about experimental petrology is just the way that you can just sort of build these pictures and then crystallize the moon in a lab, basically. I think that's pretty awesome, really.
It does make things a lot easier to visualize compared to just a graph or something like that.
Yeah,
So, yeah, that's cool.
We were talking last week to Josh Snape about some of the cool textures you get when you do this kind of stuff. I guess so. We must have some pretty nice pictures and SEM imagery and all that kind of stuff with some of these samples.
Yeah, most of the nice photos unfortunately come from failed experiments though, because when you're trying to quench them, obviously you can't directly extract something if it's at 2 GPa of pressure. So you basically have to just turn off the heating element, and then it will cool at about 200 Celsius per second. But that's slow enough that you can get some really fine scale X solution of particularly the melt phases. And so you get these really nice sort of linear patterns, like shooting out from edges of your sample assembly. Or that's a failed experiment, but
yeah,
it looks good.
So how long does it take to do an experiment from weighing out your oxide powders through to getting your, I guess, SEM or your microprobe type compositions?
So probably about 5 working days in total.
Oh, okay.
Mm-hmm.
Obviously, you do more than one experiment with each starting composition, so it might take you a few days to weigh that out. The experiment itself, at high temperature at least, will only take about 2 hours.
Okay.
And then it's just as quick as you can get time on the microprobe.
That's a really rapid process then, I guess, isn't it?
Yeah, especially compared to what it must have taken in real life, I suppose.
Oh, definitely. But I mean that can change quite a lot, because I mean an experiment down at 700 Celsius or something, you might need to run that for a whole week.
Yeah. How big are some of the charges you're doing?
So the charge, I used a graphite capsule, so it had a 1 millimeter internal diameter, and it was a 2 mil tool.
Wow, okay, that's really small then, isn't it?
Yeah, I mean, so the charges are quite small, and that's because you need high pressure.
Yeah.
And obviously,
Okay.
pressure is forced divided by area, so the smaller the better.
So yeah, as someone who doesn't do experiments at all, what do you begin with? I mean, I can cook, so if you maybe explain it in that way, or I'll try not to make a pun about baking and your surname. What does this look like? How do you mix together these starting compositions?
So you literally just start with reagent grade oxides, so iron oxide, whatever. You weigh them out in the appropriate portions. And then you set the FO2, which is the oxygen fugacity of the mix, using a 1 atmosphere gas mixing furnace. And then you take that composition, you have to keep it dry. And then it's sort of all nicely powdered up, and you put it in the sample assembly.
And away you go.
Yeah. Exactly.
Yeah. So is that quite difficult to control the fugacity of the system?
Well, sort of yes and no. It kind of depends how precisely you need it. In a 1 atmosphere gas mixing furnace, it's really easy, because the gases you have are in excess, and you can just put in whatever you want, and you set the temperature. The second you take it out of that, you either want a buffer, or you want to preset the system and be confident that it's a closed system. In my case, because I used a graphite capsule, I'm effectively limited as to how high the FO2 will be, because if FO2 is too high, then I'll just make carbon monoxide. So the real difficulty in controlling the FO2 is making sure that your buffer is separate from your experimental reagents, and they don't interact in a way that will either ruin the experiment or ruin the analysis.
So once you've done your experiments and you've analysed them and you've got compositional data from them, were you comparing them to natural samples yourself, or were you comparing them with literature data?
So originally I'd hoped to compare them to natural samples myself, but in the end, mainly due to time constraints, I did it with literature data instead.
Yeah, because I guess talking of time, I suppose. I mean, when did you finish? I guess did lockdown and the pandemic and stuff affect your access to the labs and all that kind of stuff?
In some ways, the lockdown was quite well timed. As the lockdown started, I was pretty much done with my experiments.
Well, that's lucky then. Yeah.
So
a
I
perfect
just wrote up.
Yeah, a perfect opportunity to bunk it down and write.
Oh yeah, it wasn't massively fun, because especially in the first lockdown, we couldn't go into the department.
Yeah.
So it's just you wake up, you rotate 90 degrees, and
get cracking.
You're at work.
Yeah. Yeah.
So, good times.
So what were the main findings that you got when you were comparing your experimental results with the literature?
So I guess I should say that this isn't published yet.
Mm-hmm.
The
Okay.
manuscript's in prep.
Mm-hmm.
But basically I find that there's no requirement to enrich the lunar starting composition compared to Earth with any refractory or other elements for that matter. But it's a kind of a negative test rather than a positive test,
Mm-hmm.
insofar that it doesn't mean that the moon is made from the Earth. It means that
You can't rule it out, I guess.
exactly.
Yeah. Well, I think those kind of results are still just as important, aren't they? I mean,
Yeah, I mean, so you can obviously use the Occam's razor, and you can say, well, this is a simpler solution, so this is the truth.
yeah.
But I'm not sure if it's necessarily a simpler solution.
Well, no, but I think, it means that, I guess when you look at the literature, people always talk about the handful of different starting compositions for the moon that have been around for like decades now. And I guess what your work shows is that actually maybe we should be considering more terrestrial like starting compositions as well, when people go off and do all their various modelling and stuff, and that we shouldn't discount one batch of starting compositions necessarily.
Yeah. Yeah.
So there's definitely still value in there. We get references out of it for sure.
Hope so. That's the dream, right?
So as someone who's not really familiar with this area of research, how do people estimate the starting composition of like the Earth and the Moon in the first place? That's probably a big question. If you'd like to send me a PhD thesis after this, that would be great too.
So there have been sort of a few different methods. So the first one, and I think this was more common, sort of immediately following the return missions, was to take basically groups of different mare basalts and estimate or find in other ways parental compositions, and then find places where those parental places in compositional space where those parental compositions can all be related back to.
Okay.
There are other sort of estimates based on this is a real quiz for the introduction of my thesis. They base it on isotope ratios, which were taken from mare basalts, and then they sort of further apply some density constraints that we could measure. Like we have the density of the moon, and in that way sort of infer core sizes and all that kind of stuff, and then you just add up those different groups of masses.
Okay, so sort of based on the samples, trying to work backwards based on how we know terrestrial material would behave.
Yep.
Okay.
Basically, if you can think of a way to estimate the bulk composition of the moon, it's been done.
Oh, okay.
Everything's been tried. Every isotope system used it as a marker. That I can tell. So.
So, are you continuing that work now, or?
No. So my postdoc is a pretty big jump away from. So I've gone from doing pure experiments to doing experiments as a bit of a side thing, and mainly doing some SIMS work. But it's not on the moon; it's on meteorites. It's on the entitite chondrite group of meteorites. But hopefully, we're gonna, in the later stages of this postdoc, expand out from the entitite chondrites and try and look at halogens in lots of different groups.
Yeah. Will you be quite sad to leave the moon behind?
In some ways, although it's always in my heart.
I don't know about you, but every time I look up in the sky, I just think of papers I haven't written. It's a very depressing
Really?
experience now looking at the moon. Yes.
See, I have like basically the complete opposite thing, which is every time I look up at the moon, I'm like, I've got bits of that. I've looked at bits of that. That's a really long way away. And it fills me with hope. But it's nice to know that gets beaten out of you. That's good.
That's good. Yeah.
I look at it and I go, "Tell me your secrets, please." Good to know we all have different and very sound reactions.
So why particularly entitite chondrites then? What is it in? What phases in them are you looking at?
So in particular, I'm looking at the mesostasis or the glass. So we're basically trying to estimate halogen inventories of anesthetic chondrites,
Mm.
and the probably easiest / best way to do that is to look at the phase which contains the most of them, which
Mhm.
is the glasses
Yeah.
and the chondrites.
The mesostasis, as you said in the
Mesostasis.
bit we just cut out. Yeah.
Yeah.
Which I guess the mesostasis, for those who may not be too familiar with that term, I guess it's the final sort of dregs of solidification, isn't it? I suppose?
Exactly, yeah. Once most other phases have crystallized, you get sort of a dustbin of elements which
Yeah.
don't like to go in any of the phases which have come out already, and in that group is the halogens.
Yeah, yeah. I'm a big fan of mesostasis in general because I think the lunar ones are really cool because you get immiscible liquids forming and when you get down to those kind of compositions, it's, I don't know, just quite novel, I guess.
Well, I actually, for about a week or so, I was looking into that because of the anesthetic chondrites,
Mm-hmm.
because there are 2 liquid phases, and I was talking to Rian about that last week. Based on how they're distributed, it's more likely to be a kind of either condensation or evaporation
Mm-hmm.
related change in glass composition than an immiscible.
Yeah.
But the barrier between them is like really sharp.
Yeah.
Mhm.
So
Yeah, I guess that's the thing. Like, a lot of these fields, I guess, aren't tremendously well constrained, or certainly for like where immiscibility occurs in lunar samples. I don't think it's very well constrained in terms of phase diagrams and stuff.
no, well, experimentally looking at immiscibility is a sort of a career graveyard in a lot of ways. It's
Yeah?
quite difficult to experimentally recreate.
Really,
Mhm.
it's
And
interesting.
And so from the Daily Gap, there's a 1914 Daily paper which looks at 2 different sort of large groups of igneous rocks,
Yep.
and suggests in some ways that immiscibility might be the reason that they separate. It's sort of come in and out of sort of publishing fashion through the years.
But why is it difficult to recreate experimentally?
Because even if you have 2 experimental liquids which are stable, they don't necessarily split.
Mm-hmm.
Because while they do sort of at the very small scale split, you need them to split and be big enough in area that you can get a clean point on them when you're looking
Mhm.
at them.
Yeah.
So you don't know if you're in the immiscible phase area of the phase diagram, because you wouldn't necessarily produce 2 different blobs which are big enough to see
Mm-hmm.
even under a E-beam
So it'd just
instrument.
be really fine grained, basically.
Yeah,
Yeah.
and also
interesting.
it's not like when they're immiscible, one is 50% and the other is 50%, right?
Mm.
You can have like a tiny little,
Little bleb. Yeah.
really high SI or really
Yeah.
high FE
Yeah.
immiscible blob.
Yeah, that's interesting.
So, where are you up to with your work here in Manchester? How's it going?
Oh dear.
Sorry, we'll cut this out.
Oh no, I mean, it is going pretty well. I'm currently struggling to try and get some SEM backscatter images of some meteorite slides I'm trying to analyze. And once I have those, I need to get some probe data on the mesostasis for internal standardization for SIMS. I'm going to Nancy, I think it's pronounced, in France in December. And I need to have backscatter maps to do targeting for the SIMS, and then EPMA data for the standardization. And I currently have neither.
That's pretty cool. You get to go to France, though.
I mean, yeah, it's awesome.
Oh, looking on the positives, John. That was
It's
lovely.
awesome. Yeah.
So how many samples have you got at this stage?
So there are 7 meteorites,
Mhm.
and I think I have 14 slides. Although most of those meteorites, I only have 1, and then there are 2 that I have a
Right.
lot more for. So I'm currently trying to get some probe time, basically.
And so how, because I guess you've been in Manchester now for a couple of months now, I guess. How
Yeah.
have you found transitioning from one field to another?
It's been a bit of a learning curve.
Mm.
It's also different in terms of when you're reading a paper and you've been doing experiments for quite a while. You're sort of used to all the lingo. You're used to looking out for certain things that you think are important or not
Mhm.
about a particular study. And when you transition to looking at meteorites, in my case at least, you're sort of not just using a lot of different vocabulary, but you're also looking out for different things which you think might be key in this new field.
Mm-hmm.
So it's almost felt like I've started a PhD again, if I'm completely honest,
Yeah.
Yeah.
because it's been a pretty steep learning curve. But it's quite enjoyable.
Yeah, for sure.
And it's really nice working with an actually natural sample,
Mm.
because whenever you're doing an experiment, in the back of your mind, you have a lingering question, which is this really what it was like?
Yeah.
You see what I mean? Is it definitely this?
And you got the
Because-
opposite problem though, because you know it definitely was like that, but you've not necessarily
Yeah.
any idea how it happened.
Yeah.
Yeah, particularly when you start looking at like really messy, brecciated and rubbish-looking sections.
Oh yeah. They're also much more difficult to polish.
Oh yeah, yeah, I
Mm.
can
Lots of
imagine.
different phases of different hardnesses.
Yeah.
Experimental sample, nice soft graphite,
Mhm.
outer capsule, lovely. Polished that in about half an hour, but no.
Yeah. So how did you get into planetary science in the first place? That's just sort of changing track slightly, I guess. So you said you did your undergrad in Oxford.
Yep. So my master's was in the XPET lab. That was looking at manganese speciation as a function of FO2, and then trying to apply that to like a large data set of morbs.
Hmm.
Okay.
And I really enjoyed experiments. I thought
Yeah.
it was great. Quenching a 1 atmosphere experiment is spectacular, because you just run a fuse through the wire that holds it,
Mm-hmm.
and then you have a little ball of 1600 Celsius glass just dropping down
Into water or
Oh,
something.
yeah.
into DI water.
That's cool.
But it's so bright. It's
Yeah,
awesome.
I've
It's
seen.
like a personal firework.
Yeah, it's awesome to just to watch it. And
Yeah.
I thought it was really cool. And there was a project looking at lunar basalts.
Mhm.
So funded by the STFC.
Yeah.
So I sort of fell into it because of experiments, and here I am.
Here you are indeed. Yeah, that's cool.
Was that just geology or earth science you were doing then as your undergrad?
Yeah, Earth science, but I think it's all the same,
Mm.
pretty much.
So I feel like we've told quite a neat story from
Mm.
your PhD. Like it sounds like it's, very smooth, as I'm sure lots
Yeah.
of PhDs do sound in hindsight. Were there any other, cool bits of work that you did along the way?
Well, in 2018, I got to go to Japan to work with Professor Takashi Yoshino in Misasa Institute of Planetary Materials, and that
Cool.
was brilliant to sort of get into a new lab. And
Yeah.
the Planetary Materials Institute in Misasa is absolutely incredible. It's easily by a long way the best equipped
Mm-hmm.
department and lab I've ever been in, and it was awesome. Like I got to meet quite a few new people.
Yep. Yep.
Um,
So was that like an internship type situation? Or?
Yeah, it was. I think it was called a summer student program.
Okay.
We did some multi-anvil experiments, and the actual multi-anvil we used was awesome. It was about 3 stories tall, and it was. So that was with even smaller samples with an even bigger machine. So we were going up to. Well, we did an experiment up to 25 GPa, but we.
So that's for real high pressure type stuff.
So
then?
that's like mid mantle.
Yeah. Wow.
Kind of pressures.
That's cool. So
And-
what sort of things were you like? Was it terrestrial stuff? No, your planetary stuff. I guess.
So that was all terrestrial. So that was looking at dehydration of iron and aluminium oxyhydroxide minerals in subduction zone conditions.
Oh right.
Mhm.
Wow. Okay. Cool.
It was basically trying to figure out whether these minerals could be carriers of water
Mm-hmm.
into the
Okay.
deep mantle.
So say that again. The minerals were.
So iron oxyhydroxide and aluminium oxyhydroxide. So it's goethite
Ah right. Okay.
Mhm.
and I can't remember what the aluminium
Yeah. But okay.
just
But that kind of
diaspor.
that kind of hydrated. Okay. So what I guess what are these just like sort of sediment stuff that's on the seabed that's being subducted, or is
Yeah,
this
so,
like...
so these are found at shallow depths
Mhm.
in the subducting plate. And the question is,
do they contribute water?
can
'cause-
they
yeah.
subduct water?
Yeah,
Is
because
it possible for water to be subducted in general through these minerals?
Yeah, because I guess is the classical view then of water being dragged back down into the mantle that it's all sort of dehydrating from the actual slab itself rather than from the top lying sediments or whatnot.
So basically, the question comes because there are some very high pressure phases which can hold water at deep mantle conditions.
Yeah.
And obviously, we know that there are some low pressure phases which can hold water. And we were just trying to sort of bridge that gap to see if
does
you
one
actually
turn
get
into another?
stuff
Yeah.
all the way down until it is stable.
Yeah.
Subduction zones are kind of weird because as the slab is subducted, it depresses temperature.
Mm-hmm.
So you're sort of dealing with quite high pressure, but not necessarily
high temperature. I guess it's all being fluxed, isn't it? I suppose. Or yeah. That's cool.
And well, the basic conclusion was no. Certainly not at the current in its current configuration. Oceanic crust wouldn't be able to subduct water.
Mm-hmm.
Okay.
But there's a kind of open question in the past, because in the past, while mantle potential temperature was higher, and so the actual temperature of the thing is higher, also the thickness of mid-ocean ridge crust is thicker, and so it would sink more quickly.
Mm-hmm.
And obviously, as it's sinking, you're conducting, so it's a conductive temperature gradient, which is quite a steep temperature gradient. And so if it's the case that the ocean crust can subduct quickly enough, you wouldn't be able to conduct temperature in quickly enough to dehydrate these phases. So while it's not possible under the current in the current mantle, it doesn't necessarily mean that it was impossible in the past. There are sort of factors on both sides in that.
Yeah. So basically what you're saying, I guess, is that the minerals, they just sort of dehydrate before they get to a point where they can be stable again.
Right now, yes.
Yeah. Okay, that makes sense. Yeah, cool. Oh, that's interesting, though. Yeah.
It's a very cool experiment. You basically get to drop a building on a tiny sample.
Yeah.
Oh, yeah, those things were awesome. They took... I mean, the only annoying thing about doing such high pressures is that it takes quite a long time to compress.
Yeah.
But that's for safety reasons as many as others.
Well, yeah, I'll bet. You wouldn't get your finger stuck under there, would you?
Don't think you wouldn't be recognisable as that anymore afterwards. So.
Your diamond finger.
Yeah.
Yeah, no, that's cool. So, but I guess obviously you're working with much even smaller sample volumes there, as you said. I mean, does that get, when you start to get to such small volumes, does it get difficult to interpret the textures and stuff like what you're seeing, or is it all chemistry?
It does get a little bit more difficult. It is mainly just chemistry, though. Although in this set of experiments, we were just looking for the presence or absence of a single phase.
Right. Okay. Yeah.
So it was just analysed with XRD, and then we just looked to see if the peaks were in the right place. So that in that case, the analysis was fairly simple.
Yeah.
And actually, you could we could pretty much tell before we used the XRD machine, because when you extract your sample from the sampler assembly and you're polishing through, you can see the water that comes out.
Oh, really? Oh,
so
wow.
if it's dehydrated and you're grinding it dry, the pad will get wet.
Oh, that's cool.
So obviously that wasn't used as an actual test.
Yeah.
but you could pretty much grind it down, and if a liquid came out, it dehydrated.
Yeah. Well, yeah.
But yeah, that was awesome.
How much water are you putting in the first place?
So the only water that's put in is in the mineral phase.
Mm-hmm.
So if you put in iron oxyhydroxide goethite, I don't know, probably a few weight % water.
Yeah.
So
that's pretty neat.
Much less than a gram of sampling.
That's a very cool project, I have to say.
Yeah, that's like one of those fundamental earth science questions. That's really cool.
The most awesome thing about that project was watching the professor who supervised me, and the partner in this project was someone called Kyle, who's from Princeton, who I work with there, and Takashi Yoshino was our professor. And I'm not used to making all the components that in Oxford, where I did my PhD, it was made on an AutoCAD machine, basically.
Mm-hmm.
But in Misasa, they made it all by hand. And so you're making like MgO, like a crushed magnesium oxide ring, which you use as like a spacer to keep all the sample in the right orientation and in the right place. And that might be 0.5 mil wide. And you make it on a lathe, and Takashi Yoshino would just be... It was incredible.
Just lathing away.
I would have let that guy do brain surgery on me. It was unbelievable.
How do you even see that? Do you do it under a microscope or something?
So I did it under a microscope.
He's just got crazy eye, crazy.
He's just got crazy eyes.
he was unbelievable. He was so hardworking, and he was. It was such a fantastic culture there as well. Mm-hmm. At 2 p.m. every Friday, the highest professor and the lowest intern, me, they, banged a dustpan and brushed together and everyone cleaned the lab.
Oh,
that's cool.
And it was brilliant because the lab was clean.
Yep.
And it's way easier to work in a clean lab.
Yep.
And the fact that you made sure you weren't going to the toilet at 2 p.m. on a Friday.
Yeah.
Because you had to be there to clean the lab.
Mm-hmm.
Oh.
And it just made it such a good working environment.
Yeah.
Because everyone was, courteous and and clean. And
that is quite different to here.
Unlike here in Manchester. Yeah.
Well, yeah, because you were impressed that I wiped the table before we started recording. It was very dusty.
I'd like to stress that the labs are clean.
Yeah.
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 Oh, that's great. Are you still involved with any of that work now then?
No, it was just a summer project. Mm-hmm. But my admiration has not, as I'm sure you guys can tell.
Yeah. No, it's cool.
Yeah,
That's awesome.
it was a.
Oh. Swell.
Cool. Well, we're just about out of time here, more or less. I suppose we should start wrapping up. So we have one customary question that we ask all our guests. Which in fact, I don't think we've asked this question for a while now, have we?
We've had some repeat guests on, so we've not asked them again.
That's true. But basically, Ed, our final question is always, if you didn't continue in academia and you hadn't chosen the route of chondrites or lunar science, what sort of thing do you think you might have ended up doing?
Scuba diving instructor.
Yeah?
Ooh.
Great answer. I respect the conviction with which you delivered that as well. That was immediate.
When I went to undergrad, I decided this when I went to the interview for my undergrad.
Mm-hmm.
I was like, I didn't look around before I applied. I just thought, I've got a spare space in my UCAS form. I'll stick down Teddy Hall in Oxford. And when I went to the interview, I was like, you know what? Worst comes to worst. I'll just become a scuba diving instructor on a tropical island.
Yeah, fair enough.
And, let's be honest, those guys have made it.
Yeah.
So do you do much scuba diving then, or
no?
It's purely aspirational.
It is purely aspirational, but
that's good.
I feel like I could do it.
Yeah.
I'm not sure about, because you have to have good ears and stuff so you can clear them, and I'm not sure about that.
Yeah.
And it's probably quite difficult in a lot of ways. I can also imagine myself freaking out if my mask started to fill up and you were underwater.
Mm-hmm.
Yeah.
And I know that you can't just go straight to the surface because you get, bad stuff. Nitrogen comes out your blood and stuff.
Yeah.
But I'm
Scuba
keeping
diving.
it as the
Plan
backup.
B. And have you got a particular Caribbean island in mind you'd like to go to?
You know what? I'm going to open it, and not just the Caribbean. I'm
Yeah.
going to say any sandy tropical beach.
Anywhere that'll have you.
Yeah.
Anywhere that will have a badly trained and possibly incompetent scuba diving instructor. That's the one. Whichever islands do the fewest background checks. That's probably where I go.
Safety assured. Excellent. Well, that's very
There you
good. That's
go.
a good answer.
Thank you.
Well, brilliant. Ed, thank you very much for coming onto the podcast. That was great chatting with you.
Thanks for inviting me.
We will,
Pleasure to be here.
It's our pleasure. No, we'll be keenly following the results of your experiments over the coming years, I'm sure. But in the meantime, thank you everyone to listening. We'll be back next week with some more Earth science and planetary science content. Don't forget to check us out on all the various social medias. The links will be probably on the screen below or on the episode description somewhere, depending on how we edit this video. But yes, see you all next week. Take it easy.
Bye.
Bye.
Bye.